Oh, dang it. Okay, so when I say continuous, does it make you think of anything? You don't know what continuous is officially, but if you were trying to come up with your own way to describe something that is continuous, what would you think of? It keeps going. I like that. Any other thoughts?
End, or sometimes no definite beginning.
No end or no beginning. Okay, good. Just keeps going and going. Okay. Good. So when we talk about a graph, okay, we want to be able to draw our graph without lifting our pencil. Okay? We just keep going, right? And so a continuous curve means there aren't any breaks or holes. Because if there are breaks or holes, we can't draw without lifting our pencil. Sorry. You're fine. I just want to make sure everyone can. Okay, so this curve is continuous because it just keeps going, right? This curve is not, this curve is what we call discontinuous, right? Because here we have a break, here we have a hole. We'll talk more about what kind of discontinuities we have, and specifically what we call them, but if you can't draw your entire curve without lifting your pencil, it is not continuous, okay? What kind of curves always will we be able to draw without lifting our pencil? Like, what comes to mind first? A line? Cosine and sine. Anything else? Parabolas. Good. Let's keep going with, like, we have linear, parabolas. We can group all those together in what family?
Functions.
Yes, functions. What specific type of functions? Polynomials. Polynomials are always continuous, right? They just go on forever in both directions. No holes, no anything. Okay? Polynomials are always going to be continuous. Okay? However, rational functions are not continuous because what do they have?
Holes.
They could have holes. They also have what?
Right.
They have some breaks. A rational function is either going to have a hole, an asymptote, or both. Okay? So if we have a rational function, we know that wherever our denominator is 0, that's where a hole or an asymptote is going to occur. That is where it would be discontinuous. And we'll talk about the difference between a hole and an asymptote, but we know without looking at a graph that a polynomial is continuous and a rational function is discontinuous where the denominator is 0. Now, on the next slide is our official definition of continuity. Okay. There's going to be 3 parts. You're going to write them down. I cannot stress how important the definition of continuity is and knowing all 3 parts. Okay. It's important. So I don't know if you want to like a little star or some sort of notation in your notebook, but this definition is one of the more important definitions. Okay? So, continuity. A function is continuous at C. So this is just continuity at a point. if we pick a specific point C, then the function is continuous there if the following three conditions are met. Okay, so we're talking about continuity at a point. Condition number one, f of c is defined. There is a coordinate at x equals c. Number two, the limit as x approaches c has to exist. Anyone want to take a shot at what the third one's going to be? Very good. They have to be the same. We need a coordinate, we need a limit, and they have to have the same value. Okay, so I'm going to give you some pictures of some counter examples so you can understand which one of these is basically missing from the picture. Okay? So here's an example of a discontinuous graph. Why? Because here at C there is no coordinate. Okay? We have the limit as x approaches C. That would exist, but there's a hole. There's no function value. It is not continuous. Okay. Here, now we have the function value, but the limit from the left and the right, they are different, which means the limit towards C does not exist. Not continuous. Okay. All right, now we have both. The limit exists, the function value exists, but they're at different places. And so we still have that hole, right, that we would have to lift our pencil to keep drawing the curve. So that would be discontinuous. Okay, does that make sense? Okay. Let's talk about some curves. Okay. We talked about, you guys gave me an example of the sign of x being continuous before you even really knew what continuity was, right? And so if I were to ask you, where is the sign of x continuous? You would tell me that it's continuous everywhere. Negative infinity to infinity, okay? It's continuous all over, entire domain. Okay. Do you guys remember this function, the step function? I like the step function. It's good stuff. Okay. As a whole, is the step function continuous? It is not continuous. We would have to lift our pencil many times to draw that graph. Okay? We are discontinuous at -1. We are discontinuous at 0. We are discontinuous at 1. However, are we continuous? Oh my goodness. write that somewhere else. Are we continuous from 0 to 1? Yes. Now, why did I write it that way? Why did I write it with a bracket around 0 and a parentheses around 1?
There's a closed dot at 0 and one dot at 1.
Yes. Okay. We have closed dot at 0, open at 1. Now, if we're talking about endpoints, okay, then that condition of the limit existing, we would have to think of just a one-sided limit, okay? Such as like over here with our semicircle, we can say that this is continuous from -2 to 2 because there's no domain to the left of -2, there's no domain to the right of 2. So we're really just talking about the one-sided limits, so we can say that it's continuous and include the endpoints. Okay? Same thing over here. We can include the endpoints if we just consider the right or left-hand limit, depending on where that endpoint is. Okay? All right. So, yesterday on your quiz, we had a piecewise function, right? And you had to figure out if the limit existed or not, right? If the limit did exist, it's exciting, right? Now, we are going to take that problem, we're going to change it a little bit. Go ahead and write down this function right here. Why does this look different? There are some A's in it. Okay. How are we going to make this continuous? What will be the process to ensure that this is a continuous piecewise function? What? Okay, so the break in the domain is at 2, and that's where we're concerned, right? Okay, we need to check the limits from each side to make sure that limit exists, right? And that limit should equal the function value, correct? All right, so let's first work on the function value. At 2, where would we plug 2 in to get our function value? The first or the second piece? The first. So that equals 4a, right? Okay, so there's our function value. We also know that if we look at the limits as x approaches 2 from the left side, we would do the same thing, right? We would plug 2 into that first piece. Okay? So our function value is the same as the left-hand limit. Let's look at the right-hand limit. We look at the limit as x approaches 2 from the right. We would have to plug into the second piece. So what can we do with that information? What? Well, we need it to exist if we want it to be continuous, right? So what should be true about the right and the left-hand limits? They should equal each other. Okay. So A is 2/3. Okay. Our function value must exist. Our limit must exist. And that was probably the most important part of this, that the limit needed to exist. right? And so in order for the limit to exist, we needed to make sure our right and left hand limits were the same, and that is how we got that A value. Now, if we plug 2/3 in for A, we would get a function value at 2, a limit at 2, and they would be the same. That will be a very popular problem, not only in the class, but on the AP test as well, okay? They really want you to use that definition of continuity, all right? Okay, let's talk about the types of discontinuity, right? We know what discontinuity looks like, right? Jumps, breaks, holes, asymptotes, all right? But there are two types of discontinuity. We have removable and non-removable discontinuity. If we have removable discontinuity, that means we could rewrite the function to make it continuous. There is something we could do to rewrite it to make it continuous. Okay, I'll show you what that looks like. We'll have a picture, all right? Non-removable discontinuity, the opposite. The function cannot be rewritten and will always be discontinuous no matter what. Okay, so a removable discontinuity would be like a graph that has a hole. Okay, now removable means we can rewrite it to make it continuous. How do we rewrite this equation to make it continuous? Okay, we can either, yeah, it's essentially a line, right? Is that what you're talking about, like the line x plus 1? Okay, we could also do this. We can make it a piecewise function to where we have this function where when x doesn't equal 1, and the function is 2 when x equals 1. We can basically fill in the hole, make it a piecewise function, okay? And you'll see that quite a bit. Right? What do you think a non-removable discontinuity is going to look like? If a hole is removable, an asymptote is non-removable. There's nothing we can do about it. Okay. Those are going to be your most popular types of removable versus non-removable. Your stair-step function has an infinite number of non-removable discontinuities. There's really no way we can make that continuous. Yeah. We don't want to try to make that continuous. Okay. All right. So what we're going to need to be able to do is take an equation and pick out whether we have discontinuities and what type they are. All right. So here are your first two equations. F of x is the tangent of x, and f of x equals 2x cubed minus 1. Write them down, and I'm going to give you about 30 seconds to discuss with your pod whether you think they're discontinuous or continuous, and where they would be discontinuous. Okay? 30 seconds.
Isn't there a value?
Okay, let's talk about number 2 first. Number 2, is it continuous?
Yes.
And how do we know that? It's a polynomial. It is continuous everywhere. All right. Is number 1 continuous? Eric, where is it discontinuous?
Every x value starting from pi, or every pi, there's an asymptote.
Mm-hmm.
I don't remember how to say it.
Okay. So we know that there are asymptotes that occur every, they're pi apart, is what you're trying to say. All right. If you want to think of it, you can either think of the tangent graph. We can also write this as a fraction, and we know that anywhere the denominator is 0 is where we have discontinuity. Okay. So if it helps, let's think of where cosine is 0. 5/2, 3/2, and it's just going to keep going, right? So we could say we are discontinuous every pi over 2 plus pi times an integer, because that means they're pi apart.
That's what I was.
Yes, and I knew that's what you were trying to say. You haven't had this notation since you were graphing, way back in January. Okay, it's been a few months, so there's your reminder. All right, so pi over 2, and then it happens every pi. All right, a couple more. Go ahead and write these 2 down. Okay, number 3 is a fraction. We know there's going to be some discontinuity, right? What do you think we should do with number 3 before we really get into the discontinuity?
Factor out the x and y.
Okay, we should do some factoring just so we are clear whether we have asymptotes versus wholes. Okay? All right. We have 2 discontinuities. We are discontinuous at x equals 0. What kind of discontinuity is that? What'd you say? It is a whole, which means it is removable. Okay. We are also discontinuous at x equals 1. What's happening at x equals 1 graphically? Is it a whole or an asymptote? It's an asymptote. And since it's an asymptote, what kind of discontinuity would it be, April? Non-removable. Okay, if it's a whole, removable. Asymptote, non-removable. All right. Okay. Number 4. How are we going to figure out if that one's continuous or not? we need to see if that limit is matching up, right? Okay. So we are concerned about the break of the domain. So the left and the right hand limits at 0. Okay. So if we go from the left of 0, will we plug into the first or second piece? So that limit is 4. The limit as x approaches 0 from the right, we're going to plug in, oh gosh, I don't know what's going on here. That's not square though. And what's that limit? 4. All right. So we can conclude, right, that the limit as x approaches 0 exists. It's 4. All right. And we can see that the function value would be the same. So we can say that this is continuous everywhere. Because it's a piecewise function that involves two polynomials, and they're meeting up. So it's continuous everywhere. Okay. All right. One last thing to talk about. The continuity of a composition. All right, so go ahead and write down these two functions, and we'll talk about their composition. Okay, so last year about this time, minus a week, okay, last year, you talked about composition functions in pre-calculus and their domain. Continuity is very similar, all right? We need to think about the continuity of the inside function and how that compares to the continuity of the resulting composite function, okay? So what's true about the continuity of g of x? Continuous everywhere. Great. Now let's look at the composition. We are taking 3x and replacing x with it. So this becomes our composition function. Is our composition function continuous everywhere, just like g of x? Nope. Where's our discontinuity happening? And what kind of discontinuity? We have long words to spell out in calculus. Non-removable discontinuity. All right, trying to remember. Okay, so I really would not worry about writing these down. Okay, these are in your book. And it's a lot like when we talked about domain last year, okay? So if we have continuity of two different functions at C, then when we combine them, we are still going to have continuity at C. Okay? Whether we multiply them, add them, divide them. The only thing that's tricky is if we are dividing by 0, then obviously it cannot be continuous there. Okay? And then we just talked about the composition. This is officially what it says. If G is continuous at C and F is continuous at the G, which is what we're plugging into first, right? Then the composition is continuous at C. If you just want to make a note that these are on page, that way you don't have to write them all down. These are on page 75, okay? Now, what I would like to do with the remainder of our time, okay, I am going to pass out some papers. And as I do that, I want you to answer this question. And you guys can talk about it at your pod. This is an AP multiple choice question. As I pass these out, I want to see if you can come up with the answer. Raise your hand if you want more time. All right. Raise your hand if your pod thinks it is A, B, C, D, E. Okay. So we're all across the board. Let's talk about this. The limit does not exist. Did you check? Oh, okay. What happens here? Right? So what's the limit as x approaches 3 of f of x? It's 6. The limit does exist. We can evaluate it analytically. Is f continuous at 3? The limit is 6. The function value is 6. You betcha it is continuous. Is x equals 3 a vertical asymptote? No. It canceled out, which means it's a hole, which gets filled in by 6 here. The answer is B. Okay? Now, you were supposed to struggle with that, but I need you to start getting familiar with the layout of these questions. You'll see questions like this a lot throughout the year, and then, of course, on the AP text. Okay? So what I'd like you to do with the last 5 minutes of class is to go through this worksheet with your pod. Get as far as you can. You have book homework you can find on your gold sheet about continuity, but there's this theorem called the intermediate value theorem, and before you learn what it is, I want you to think about a couple things. So go through this worksheet, then I'll take you to the bell. Okay?